Thank you very much, Svitlana. And thank you very much for the opportunity to speak to all the organizers. It really is a great honor to speak with such eminent scientists here. I would not count myself amongst them, but I feel like I've learned a ton. And hopefully maybe I can say something of interest to all of you. So maybe a caveat on top of Svetlana's caveat. Svitlana is very good at languages. She calls herself not an applied mathematician or a physicist, but she's learned French and she's learned how to speak physicist as well.
She's very good.
Yes, very good. I'm terrible at languages, and I don't know French, and there's no Duolingo or Rosetta Stone for physicists either. So it's possible that I won't speak the same language. But my sort of purpose here is to try to establish a common language, and so if you have questions or you think you know something by a different name, please yell at me and stop me, and we can try to figure this out. Okay, you're going to see as I go through, I'm going to pretend to be a physicist. It comes with the clothing, and I'm going to have lots of pictures, but the charade is very thin. So let's talk about the Dirichlet problem. Let me give you just a quick overview of what I hope to talk about today, and then we'll sort of get into the nitty-gritty. So we're going to talk about harmonic measure, which is a measure which measures where a Brownian motion, a random walk, will exit a domain, right? It's a probability measure. So you start at some point, you sort of move around randomly, and then you keep track of what part of the domain you hit first. This is harmonic measure. It's related to something called the Dirichlet problem, which perhaps you're all familiar with, which talks about how equilibrium is established after diffusion has already happened. So this is not a time-dependent thing. We've let things run for a long time, and now everything is spread out, and we want to look at sort of the steady-state situation. Perhaps not surprising, if you have very nasty geometry, as Svitlana showed you this morning, then what you can have is sort of hidden parts of the boundary, where even after you diffuse, somehow your diffusion process doesn't see the data in certain parts of the boundary. Maybe a little bit more surprising is that this is a characterization. If there's no part of the boundary which is hidden, then your geometry has to be nice, somehow. And then perhaps very surprising and recent, which I hope to talk about very briefly at the end, is recent work with Svitlana and Guy on higher codimensional analogs. So all of this, which I'll talk about in the beginning, will be some sort of domain, which is an open set. You know, it's space living inside of R3, you can think of. And so things enclose a volume, but we're going to be talking about analogs where I'm talking about like a curve inside of R3, so no volume is enclosed. And then things are a little bit more complicated. Okay, so let's start in the discrete model, because it's a little bit easier. You have some random walk, here's a lattice. You should think of the x's as being points on the boundary, and the circles as being points on the interior. And you can see immediately that I'm not a physicist. I made this picture myself, and it shows. But look, it's a little animation. So you walk, you go to each neighbor with probability 1/4, right? Equal probability. And there's no sort of avoiding of self-intersection. I'm allowed to backtrack, okay? And then I just keep going until I hit the boundary. And then I keep track of where I hit the boundary. Okay. Here we go. So the harmonic measure, or the hitting measure, is the probability that a random walk, which starts at some point, let's say the red point, the pole, will first hit the boundary at the green point, the target. Okay? And you can sort of see immediately that it's actually quite complicated to compute. So it's possible that after the first step, you'll hit the boundary with probability 1/4. But then, of course, you might sort of travel all the way to the left, and then travel back to where you started, and then hit the boundary point, right? And so there's, if you sort of try to set it up, which you could, you're actually going to get a system of...
It's not your computer?
No.
The beam is dark.
Wow. It was mad about the random walk.
Red light on it.
I let physicists handle that.
Ou la lampe est grillée, ou il a surchauffé. S'il a surchauffé, il va rebondir. Probablement.
Ou alors tu as réservé jusqu'à...
Ah oui, c'est ça.
Ah,
Il est vivant là.
It went in sleep mode, I think. It's after lunch it happens.
Sure. Especially listening to my voice. Yeah.
I think it's related, so it's warming time now. Okay.
Right. Actually, this is sort of a perfect opportunity because I was going to work on the board a little bit.
Yes.
I apologize. So maybe let me try to replicate this picture that I have. You know, here's some sort of boundary points. And then here are maybe some interior points. And I want to understand the hitting measure starting from this pole and getting to this target. And what I want to convince you is that this measure satisfies what's called the mean value property. So if I fix the target but move around the pole, then the probability that I first exit the target from here is equal to the average of the probabilities that I first exit the target from all four of these places, right? And you can sort of see that because what's the probability that a random walk, which starts at the pole, exits in the target? Well, it's simply the sum over all the neighbors of 1/4 times the probability that a random walk, which starts at the neighbor, exits in the target. Right? I mean, the random walk doesn't remember that it started here. So if it moves here after the first step, and we calculate the probability that then, if we keep going, we exit here. Or if it moves here after the first step, we can calculate the probability that if we keep going, we'll exit here. And when we add up all those probabilities, what do we get? But the probability that if you started here and you kept going, you would exit here first. Hopefully this makes some sense. So this is what's called the mean value property. We'll talk about it a little bit more on the next slide. So here we have this hitting measure. I'm going to use this notation, which is the little omega pole of target. Obviously, the hitting measure depends on the pole. If you're further away, then somehow you're less likely to exit from that target. And it's hard to compute. If you really wanted to solve what the hitting measure would be, in this situation there are 10 interior points, and so you have to solve a system of linear equations with 10 variables and 10 unknowns. And so maybe if you're a physicist, that's not hard. But if you're a mathematician, this is impossible. So somehow, this is difficult.
Bringing us down below a billion equations really gets us mad.
Yeah, it's, it's too hard. And then it's the average of the neighbors, which is exactly what I was trying to do on the board over here. Okay? So functions which satisfy this mean value property, i.e. their value at a point is equal to the average of its values at all the neighboring points. These are called harmonic functions, discrete harmonic functions. And here's a perfect example. I didn't solve the 10 by 10 system of equations. I first filled in the numbers randomly in the red points, and then I made sure that the blue points worked the right way. So the red points satisfy the mean value property, and the blue points I get to pick because they're on the boundary. Okay? So there's a uniqueness here, which mathematicians call the maximum principle, and maybe physicists do too. The idea is that if you have two harmonic functions, which have the same blue values, they have to have the same red values. And this is because if you're a harmonic function, you're equal to your average of your neighbors, which means that in no interior point can you be the largest or the smallest, right? Because you're an average of other values, and so you can't be bigger than all of them or smaller than all of them. And so if all the boundary values are 0, then the entire thing is 0. Okay, so this is very different, for example, than eigenfunctions of the Laplacian, where you can have boundary value 0, but you can actually have behavior in the interior. Okay, so if I just start with the boundary, if I didn't cheat, and then I ask to fill in so that I satisfy this mean value property, this is what's called the Dirichlet problem. And you can solve it using this harmonic measure, which I talked about on the previous slide. So essentially, if I want to know the value of the fill-in at some interior
You
point,
never said why you call them harmonic, or maybe I fell asleep quickly.
Well,
I've never said why I call them harmonic.
Yes.
Because they're
Why you
harmonious.
mathematician? Why you
Why
mathematician?
me as a mathematician?
It's
Yes.
the harmonious property.
Yeah.
Value property.
It's, you know, in sync with its neighbors. I'm actually not sure why mathematicians
This is
call it.
why,
Is this really
because
it?
it's the harmonious property.
Oh, okay.
It's the
Oh.
property.
Really?
Perfect.
Yeah, really.
I thought it was because Fourier introduced
Yes.
them to solve the harmonics, the real.
For us, harmonic equals Fourier.
But that's
Yes.
very, very complicated. But you see, that isn't quite it, because the harmonics are all those things that satisfy the eigenfunction equation.
So maybe I've been warned about this, which
Guy,
is
what do
that
you say about that? Guy uses.
he was the one who warned me about this, in fact.
The word harmonic analysis,
Harmonic analysis.
it has to do with, is Fourier analysis.
Yes, Fourier.
or-
This is
or-
what we think.
Yeah,
We
absolutely.
as physicists.
But this word harmonic function
Yes. So,
is
Maybe you
sort
should
of
write a
different.
PD.
so I'm going to write a PDE in a second. So we're going to go from discrete to continuous in just a second. But I was warned that if I talk about harmonic functions in front of physicists, you will think eigenfunctions or spherical harmonics. And that's not what's going on here. This is a slightly different definition, if you will, of harmonic
Think of a
functions.
harmonic oscillator, that
Yes.
is to say.
So let me just talk a little bit about this. If you don't want to call it harmonic, you don't have to call it harmonic, right? So there are these boundary values, and I want to know how to come up with a function that satisfies this mean value property, this thing right here, with these boundary values. And indeed, it's just an expected value. For every point, I sum over all the boundary points of the value that I've been given at that boundary point times the probability that my random walk will first hit that boundary point. Okay, now if you're a physicist, probably you want a reason why this is true, but if you're a mathematician, I can just give you a proof. And so I'm just going to give you a proof. Remember, there's a unique fill-in for these boundary values. And remember that when we change the pole of these harmonic measures, we satisfy the mean value property. This was this computation that I tried to do here when the projector was out. So, this function u, defined in this way, satisfies the mean value property. Because here's the only dependence on the point, and this satisfies the mean value property. And it shares the same boundary values here, because of course, the probability if you start at a boundary point that you first hit the boundary at that point is equal to 1, right? You're already there, so there's nowhere else to go. And so this is the unique solution to the Dirichlet problem. Okay, and here's the sort of connection between probability and the PDE, which we're going to see on the next slide. So hopefully this is somewhat clear. So this is an expected value, which is kind of cool. It's a nice connection here. Okay, so let me now move to the continuum, where there's actually a PDE, and I feel a little bit more comfortable, but perhaps you feel less comfortable. So in this situation, if we're really living inside of space, then the mean value property is asking that if we take an average of a function inside of some ball, it's equal to the value of that function in the center of that ball. And if you satisfy the mean value property, that means that your Laplacian is equal to 0, right? So the sum of your pure second partials are equal to 0. I write this formula not because I think that you might not know what the Laplacian is, but because I want to make it clear that as a mathematician, I don't really care about a coefficient of diffusion. And for me, the Laplacian will be with probably what many people will call the wrong sign. So this operator is not a positive operator. You need the negative sign in front of it for it to be a positive operator. Okay? And the fact that this mean value property is equivalent to the Laplacian equal to 0 is not particularly obvious, but is also not particularly hard to prove. Okay, so here's a sort of easy example, x squared minus y squared. And again, I bring this up not because I don't think you can compute it yourself, but rather to sort of contrast the behavior with x squared plus y squared. Note that harmonic functions don't have any local maximums or minimums, right? Because you satisfy this mean value property, you can never be largest or smallest. And this is sort of important. That's what the picture is going on here, is saying. Okay. And again, this sort of represents equilibrium after diffusion, right? We've seen the wave equation and the heat equation being written down 100 times. But if u doesn't actually depend on t, then all you have is Laplacian u equals 0. And that's what's going on here. Okay. So let me try to tell you what hitting measure is, what harmonic measure is in the continuum. So all the good pictures I've stolen from someone else, and all the terrible pictures I've made myself. So you can tell easily, even without the photo credits. So you start at some point in the domain, and you run a Brownian motion, which is just walking around randomly. And then you keep track of where in the boundary of the domain it exits. And this is the harmonic measure, starting at x, of some subset of the domain E. And if you want to solve the Dirichlet problem, which is asking for a function that satisfies the mean value property in the interior, and which is equal to some specified data on the boundary, then in fact, the harmonic measure allows you to do just that. And again, this is an expectation, right? I take the boundary data and I average it against the probability that I hit that point on the domain. So it's just like in the discrete setting. And what's the physical interpretation? Here again, I pretend to be a physicist. So I heat my sort of weird shaped plate on the edge of it to some specified temperature F, and then I wait for the heat to diffuse into the interior, and then this formula tells me what the temperature is at the point X. Right? Great. Fantastic. Okay. So, as I was talking about in the overview, it's possible, of course, that harmonic measure doesn't sort of see every part of the boundary. You can hide parts of the boundary from these Brownian motions, from these random walkers. And indeed, here's a pretty easy situation where parts of the boundary are hidden. If you start a Brownian motion here, there's no way that you could first exit the domain over here, right? I mean, you have to exit it somewhere here first. But of course, this is sort of too strong. But even if you aren't completely disconnected, but you have a sort of long corridor, this part of the domain is still hidden from Brownian motions over here. It's much more likely that you'll exit the domain somewhere in this long corridor than you are to get all the way down the hallway, right? You should think of Brownian motions as sort of being like drunken walks, and it's very, very hard to drunkenly walk from this part of the atrium to that part of the atrium somehow without bumping into something. Cusps are also very difficult for Brownian motions. It would be very hard for the Brownian motion to get all the way over here without bumping into some aspect of the cusp over here. Okay? And so what? Why do I care if Brownian motion sees large sets of the boundary or not? It's a good question. Well, I'm trying to solve this Dirichlet problem. And now I'm going to introduce a little bit of notation. So I have my Brownian motion, and I have sigma, which is going to be the length measure on my boundary. Okay? It just tells me how long the boundary is. Or if I'm in higher dimensions, it tells me the surface area of the boundary, the volume of the boundary, or something like this. And I'm going to write the Brownian motion as some weight times the length measure. Okay? And now, if at some point my weight is small, if there's some part of the boundary which has long length but which isn't seen by Brownian motion, then even changing the data a lot on that part of the boundary won't change the temperature distribution very much, right? So in some sense, you can think of this, now I'm going to get myself into trouble, as maybe some sort of localization in some sense. What you're saying is that large changes in geometry can still affect small changes in the PDE, and vice versa can happen as well. That if this weight is very, very large, then even changing F by a little bit, changing the initial temperature on the boundary by a little bit, can change the temperature in the interior by quite a lot. Okay?
Yeah, acoustic wall is basically that, right?
Hmm? Yeah, an acoustic wall is essentially this,
that.
right? An acoustic wall tries to make sure that K is as small as possible and as many places as possible. So even when you're hitting the wall with a lot of noise, as it sort of dissipates, as it diffuses, it has very small value everywhere. Is that a reasonable thing to say? Fantastic. So here's my picture for the slide, right? Even if I do a big change of data here, even if I heat this up to a very high temperature, the plate won't get very hot over here. Again, because the Brownian motion sort of can't start from here and see what's going on over here. So if you care about sort of quantitative well-posedness, as mathematicians would say, of this problem, if you care that small perturbations in F should only create small perturbations in U, then you care about this mysterious harmonic measure. And that's sort of how I'm trying to sell it to you. Okay, and this is actually really a theorem, that you're sort of quantitatively well-posed if and only if this kx is not too large or too small too often. And for the mathematicians in the audience, we have a name for this. This is called being an A infinity weight. But if you're a physicist, don't worry about it too much. I think not too large or too small too often is a good description of what I'm saying. Okay, great. So let me give you a couple examples so you can maybe get your hands on this a little bit. Okay, a disk, a Lipschitz domain, which is a domain with corners, not necessarily smooth, but it doesn't sort of curl up on itself, and a snowflake. So for the disk, harmonic measure is really just proportional to length. Okay, this factor underneath here just turns harmonic measure into a probability measure, right? We want it to have measure 1. And for a Lipschitz domain, the K satisfies this not too small or too big too often criterion that I was talking about on the previous page. So when you heat a Lipschitz plate, you change the temperature pretty much proportional to the amount that you've heated it by, in average. But for a snowflake, okay, and this I did to appease the physicists and enrage the mathematicians, this K is actually equal to positive infinity or to 0 at every single point. So in some sense, the set which Brownian motion sees has length 0.
You might want to say what's the snowflake. I'm not sure. We can see.
Yeah.
Oh, is this not? Okay, maybe not. So this is a fractal. It's a Cox snowflake, and it's a self-similar set. So if I could zoom in, but I don't have that technological prowess, let's say over here, it would look exactly the same as sort of the scale 1 picture as you move further and further in. And if you look at one of these sort of little angles, it's not so obvious from the picture, but you actually have to twist sort of infinitely many times in this direction and infinitely many times in this direction to sort of get to the edge of most of the points on the boundary. And this is sort of why harmonic measure and surface measure don't talk to each other at all in this situation. So I introduced this particular example not because it's so important. You don't see snowflakes so often, at least in Paris, but in Boston you do. But because I sort of wanted to tell you that if you have nasty geometry, you can have nasty behavior of this function K. That's sort of the upshot. And indeed, I talk about it right here, right? So we have these long corridors and cusps, but they aren't the only problems. The fractal has no long corridors or cusps, and yet still there's sort of misbehavior between surface measure and harmonic measure. And so there are 2 questions. The first question is, if for some value of nice, if your domain looks good, does that mean that you have a nice K? And the free boundary direction is, if for some reason you have a nice K, if you know harmonic measure and surface measure talk to each other nicely, does that mean that the domain in which you're wandering around is nice? Okay? And there's lots of works. I tried to find someone whose name began with every letter of the alphabet, but I missed a couple. And I had to use myself, which was a little bit disappointing.
You start with the fields model just in case.
Yeah.
It's too bad that Wayne didn't
Yeah.
write something.
Right? It'd be really good. And maybe I can sort of throw, okay, so this is a very active area of research. It's been researched since the beginning of the 20th century.
By alphabet.
Okay, so there's a complaint that some of the more obvious names are not here, but I sacrificed obviousness of names for appeasement of people in the audience. There's, a little bit of trade-off.
That's cool working.
Are you his mentor?
Okay, maybe I'll skip this complex analysis business. When did I start? 45?
40 minutes, so you still have half an hour.
Ah, perfect. Okay. I won't abuse your time, don't worry about it. We're more than halfway done. So let me introduce 2 characters that have actually shown up also earlier today in various different talks. And then I can go back to the questions that we talked about on the last slide and address them a little bit more. But maybe this is a good time to stop and ask if I've completely lost people in translation yet. No? Yes, please.
Yeah, I have one question.
Sure.
You briefly mentioned the...
Charlotte,
So,
you might introduce yourself.
I'm Jean-Marie from the Laplacian. The relationship between the random walk problem and the mean value property, right? And the equation Laplacian of u equals 0. I think Svitlana tried to explain me once, but I didn't get it. Maybe you can explain now better. How you get from one?
Sure. So maybe, okay, I'm going to try to explain this physically and perhaps fall flat on my face. But you have a diffusion, right? Which means things are sort of spread out as evenly as physically possible. And in some sense, then maybe it makes sense that you satisfy the mean value property, right? Because what are you saying? If you're equal to the average of all the stuff around you, then there's no way that you could sort of smear things out more and be more evenly distributed. So in this way, sort of Laplacian U equals 0 and the mean value property talk to one another. And then the random walks come in a sort of funny way. It's because random walks sort of also represent diffusion in some sense. If I understand correctly, the idea of Brownian motion is that it was supposed to represent on a particle level what happens in a diffusive process. And so somehow you can translate between the two. To be completely honest with you, at least on the mathematical side, there are very few people who sort of speak both languages. We talk about the connection in talks, but when we prove theorems, we don't actually, we sort of stick to PDEs or we stick to Brownian motion. We don't translate between.
Maybe it's the right time to ask a question about that. It's is there, for all second order operator, a translation into probability?
Yes. Sort of, yes. So maybe I can say, if whenever you have something like negative div AX grad U, and actually even in slightly more generality, right? So here's your matrix A that represents some sort of inhomogeneous medium or something like this. Then there is an associated sort of random walk to this medium A, which maybe represents how Brownian motion travels through this medium. And if you play the exact same game, taking the expectation, doing the probability of exiting the domain, so on and so on and so forth, you'll get a solution to this PDE.
But this won't surprise physicists because they call this the diffusion constant. But if you have not a divergence form, do you still have a probability interpretation?
So there are a lot of PDEs out there, right? And so the answer is yes to some of them and no to others. For example, there are these jump processes, which are very interesting, where the Brownian motion occasionally just takes a giant leap and appears somewhere else. And these are associated to some PDEs, which are very sort of in vogue right now. I don't know, maybe you're driving at something in particular, but I'm not sure.
If you have a Laplacian plus a gradient term and...
yes, if you have a drift, and even if you have a potential, you can do this. With the potential, it's a little bit more complicated. With the drift, it's sort of the same idea. You should just think there's somehow now a wind which is blowing your Brownian particle in one direction or another direction, right? So the question is if you have something like plus b of x dot grad u equals 0. And this is your sort of Brownian wind. So there's something called Ito's formula, which allows you to translate between a process and this type of PDE.
But there's this very technical thing in analysis which has to do with how much smoothness you need for this to be a clean statement and when it becomes wrong.
So it can become wrong.
It can become wrong. I mean, there's a borderline case which is interesting for nonlinear problems when the coefficients depend on the function instead of being just depending on position.
A partial solution to that was the subject of a recent Fields medal in mathematics, so it's complicated.
Okay, yeah. We will stop here.
Yeah. I mean, I don't know much about this. Anyway, so, okay, are there other questions? Great, I'll introduce the two extra characters. So associated with this harmonic measure is a Green's function. Here's a picture of George Green. I learned something incredibly cool about George Green. He never went to school in England and actually learned all the mathematics he knew from a French mathematical textbook. So even though he's in English mathematics, even though he's English, you should think of him more as a French mathematical thinker than as an English mathematical thinker.
When was he?
I think this was shortly after, I want to say it was early 18th century, late 17th century. So the reason why historicals think that, no.
1820s, I'm guessing.
1820s.
Just because it would have to be after.
Yes, you're absolutely right, yeah.
Which book?
He was born 1793 and he died.
Wikipedia.
I should have copied more from Wikipedia. But if you keep reading the Wikipedia article, which is quite interesting, you'll learn that he used Leibniz's approach to calculus as opposed to Newton's approach to calculus, which is why historians think that he must have learned his mathematics on the continent as opposed to on England. So his life is a matter of much historical speculation. I wasted several hours yesterday learning about this. Anyway, so there's this Green's function. It's this positive function inside of your domain. It's 0 on the boundary, and it's Laplacian in the sense of distributions, or maybe if you're a physicist, just it's Laplacian, is equal to the Dirac delta function at y, right? So it's 0 everywhere, and then it's sort of infinity at y. In particular, for any function phi, you have this sort of representation of phi in terms of the Green's function and the harmonic measure. These two things sort of act in concert with one another. And in particular, if you want to solve an equation like Laplacian u equals f, or maybe we'll say g, and u equals f, so this happens in the domain and this happens on the boundary, then what you do is you multiply g by the Green's function and integrate in the domain, and you multiply f by the harmonic measure and integrate on the boundary. And that's a solution to this. So these two things sort of go hand in hand. There's a probabilistic interpretation, which is a little bit tricky. Basically, the Green's function says how likely is a Brownian motion starting at x to end up at y before leaving the domain. It's a little bit tricky because in dimension 3 and above, bless you, Brownian motion doesn't hit any particular point, right? It's not recurrent. And so you need to do some sort of conditioning and then taking things to 0 and so on and so forth, but let's not worry about that. Right? And it's really, really hard to compute. I mean, in the same way that harmonic measure was quite difficult to compute, the Green's function is in some sense even more so a difficult thing to compute. So this is sort of what I want to say about this object. It will come up again later. And then there's the Poisson kernel. I didn't need to look on Wikipedia to know whether or not Poisson was French. That was easy. F is K in this slide. Apologies. So I've been writing the harmonic measure as some function times the surface measure, or the length measure, and this function has a name. It's the Poisson kernel. And it's not hard to compute, at least formally, that the Poisson kernel is actually equal to the normal derivative of the Green's function at every point on the boundary. So you can compute one from the other. That's how these two things sort of talk to one another. The Green's function is hard to compute, if you believe me from the last slide. So this Poisson kernel is also hard to compute. I sort of want to keep emphasizing this idea. And so the question 2 that we were talking about before was asking if the Poisson kernel is nice, does that mean that the original domain was nice? Okay. So now note that this is an overdetermined problem. We have this Green function g, and I specified its Dirichlet boundary values and its Neumann boundary values. I said that it's 0 on the boundary and that its normal derivative is nice. Because this problem is overdetermined, that means that actually I can learn something about the domain. So that makes this question 2 even make sense, right? In some setting. And this is what we call a free boundary problem, because the boundary of the domain here is free. It's not fixed. We're not very creative at naming things in the mathematical community. Okay, great. So let me go back to the questions now that I've introduced these characters. I have the direct question, if the domain is nice, does that mean that the Poisson kernel is nice? And the free boundary question. I omitted the dependence on the poles because I got tired of writing that here. But you should think of it as being some pole in the interior. Right? So the starting place of the Brownian motion, I omitted. And the answer is yes, for essentially any definition of nice that you pick, which is great. So here's an exercise that you can do. It's a little bit complicated, but if you let yourself cheat, it's not so hard. If the Poisson kernel is constant, so if the random walker sees every part of the boundary proportional exactly to its surface measure, then the boundary just has to be a ball. Right? And you have to start in the middle. It's a little bit harder to see that if the Poisson kernel has a bunch of derivatives and they oscillate in a controlled way, then that means the domain has one more derivative and it oscillates in a controlled way. It's an interesting fact that you need the oscillation to appear here. And I bring this up not just because I'm sort of a mathematician obsessed with preciseness, but to say that this is really a quantitative result. You control the oscillation by the oscillation over here. And if you're just in the regime where you know something is continuous or bounded, but have no quantitative information, then you can't prove any theorems. Okay? So this is sort of an important thing to keep in mind. And then there was results that say that the oscillations really control one another in a very precise way. And then recently, this year, these questions were completely solved. So you don't necessarily need to understand everything that's written up on the board, but basically what it's saying is that if your Poisson kernel is never too small or too big, too often, this A infinity condition, then your domain will look pretty much flat at most points and most scales, and vice versa. So this is a complete characterization of when you could solve the Dirichlet problem, which mathematicians are interested in. And this is a culmination of at least 40 years of very, very hard work that happened, I guess no longer earlier this year, but earlier last year. So the takeaway is that the geometry of a set is completely characterized by solutions to this PE and the complement of the set, right? And maybe this is the takeaway that's most interesting for the people working on localization, is that somehow if you understand the solutions of the PDE, you can understand the geometry of the set. We've already talked about in Svetlana's talk how if you understand the geometry, you might expect to see some localization. And now this is telling you that maybe there's some hope of solving the inverse problem, which I think came up this morning. That if you understand the localization, you should be able to understand the geometry. Okay. Let me make a very quick digression into something called the dimension of harmonic measure, because it's a timely subject, because it's sort of a very famous question in the field that maybe some of you have seen before. So there's this famous open question, which is, what is the maximum dimension of the support of omega? Or said another way, it asks if the Brownian motion can see every point of the boundary. So I'm not even asking it for it to see every point equally, or for it to see every point sort of proportionally to how many points there are. I'm just asking if it can see any point at all. How many points can the Brownian motion see? And so if a boundary is a fractal like this, if it has lots of curves and winds in and on itself and then back out, the answer is not so obvious that it can see every point. There's a beautiful theorem by Makarov in the 80s, which says that if you're in the plane, like this fractal, then really you can only see a set which has sort of length, which is one-dimensional, some sort of curve. I'm fudging this a little bit. And then there's a beautiful result by Morgan a couple years later, which says that the harmonic measure can't see every point in the entire sort of ambient space. There has to be some points which are sort of hidden from harmonic measure. Morgan recently died, which is a great sort of loss to mathematics. And this theorem is incredibly beautiful and represents the state of the art even 40 or 30 years later. And then later on, there's sort of work by Tom Wolfe, which says that you can always come up with domains for which the Brownian motion at least sees things of codimension greater than 1. So you can come up with these crazy fractals in higher dimensions for which you really see things that have infinite length. You see every point. Okay, so
Greater than or equal to 3.
Yes, sorry.
Consistent with,
In this last one, n is greater than or equal to 3. Yes, thank you very much. I think Marcel and some other people in the audience have done some very interesting work on physical problems where the dimension of harmonic measure, and in particular Makarov's theorem, comes into play. But I sort of can't tell you anything about that.
We just made numerical simulation in 3D, showing that computing the dimension of omega for a specific set, and we found 2.003 by very difficult computations, which apart from n-1, significantly the error of ours is outside 2. So.
And then harmonic measure also came up in some applications to biological processes and stuff like that. So this is an interesting thing. The precise value is completely open and is probably the biggest open problem in this field, but I won't talk about that because I don't have anything interesting to say. Okay, so for the last 10 minutes or so, 15, let me abuse your hospitality and tell you a little bit about some current work in the field that I've been doing with Svitlana and Kate. So in all of these situations, right, I'm living in the blackboard, and I have some enclosed area, and I look at the Brownian motion exiting the enclosed area. So it's a codimension 1 situation. The ambient space is 2, and this line is dimension 1. Okay, and you can think of similar pictures in higher dimensions. But now I want to think of higher codimension pictures. So you should be thinking of a line living inside of R3 space. So a curve in R3, or if you want to be more exotic, you can even think about one of these fractals that I put up on the board in R3. The problem, of course, is that elliptic PDE, or if you would prefer Brownian motion, doesn't see sets of very low dimension. So if you're living inside of R2, say, a Brownian motion may or may not hit this point. Okay? In fact, with probability 1, it won't. hit this point. And so if we have this interpretation of Brownian motion, or as solutions of these PDE in terms of Brownian motion hitting things, when we go to higher codimensions, we're immediately in trouble, right? Because we can't sort of take expectations or probabilities when everything is 0. So why do we do this? Well, we're mathematicians. We do things because they're fun. This is Guy's pernicious influence here. But also perhaps there are some interesting applications to biology. I stole this picture from Svitlana, who stole it from a McGraw-Hill textbook. But the idea, I guess, is that DNA and chromosomes will sometimes sort of fold up on themselves or stretch themselves out to make themselves more or less attractive to enzymes that are floating around. And if you can think about the enzymes as being Brownian motions and sort of R3, this DNA is your thin one-dimensional set that's trying to attract the random walkers. So this could sort of be an interesting idea. But to be completely honest with you, since we're amongst friends, we don't actually have a concrete sort of experimental validation of this model. So it's still mostly fun. So you need a degenerate elliptic PDE. Or in other words, you need a way to sort of convince the Brownian motions to come towards this small set. They attract the Brownian motion, these degenerate coefficients. So here's my setup. If all the dimensions confuse you, just really think about yourself as being in R3, and then you're looking at the graph of some function which goes from R1 to Rn minus d. So the idea is that you have some sort of curve living inside of the space, right? And I'm drawing these sort of lines to try to indicate that this is a three-dimensional picture. You can go into the board and out of the board. Okay, so it turns out that if you look at solutions to this PDE, where we take our usual elliptic matrix, our coefficient of diffusion, is that what we're calling? And we make it grow larger and larger and larger as we get closer and closer to the thin set. Then solutions to this PDE, random walkers driven by this coefficient matrix, will see our thin set. So this is sort of related to Marcel's question from before, whether or not there is a probabilistic process that talks to these coefficients. We're in France, which I guess is the original land of perfume and cologne. So you could think about this as sort of the set puts on some sort of attractive cologne or something like that to attract the Brownian motions. I embarrassingly had to look up how to spell eau de toilette. So. And the question is, can we come up with a cologne such that the geometry of our set E, the geometry of this graph of a function, is characterized by the associated harmonic measure? Right, the associated hitting measure. Great. So it turns out that this function, which takes x and maps it to the distance from x to the set, is not a very nice function. And you can sort of see that right here. If your set has any sort of angle in it, then the function distance from the point to the set changes dramatically if you go this way or this way. Right? Because there's sort of this discontinuity. And this creates a lot of problems for technical reasons. So what we want to do is smooth out this distance function. And so Guy, with Svitlana and Svetlana's former postdoc, Josef Bernay, whose name I'm almost certainly butchering, came up with a family of smoothed out distance functions, which are comparable to the distance of the set. And they look like this, right? So you integrate over the set, the distance from a point to the point on the set, and you raise it to some power alpha, and then you raise it to this other mysterious power to make sure everything scales correctly. This is the idea. So, if you don't like this formula, then you can just think of d alpha as being some smoothing of the distance. And indeed, this alpha ensures that there's some sort of comparability between the two. And d alpha is nice because it sees the whole geometry, right? If you're looking at the usual distance, then if you change your set over here, the distance from this point to this set doesn't change. But now d alpha sees how you change things over here. So this non-locality is very helpful for us. Okay, and now here are some sort of technical results, which are more for the mathematicians in the room. With Guy and Svitlana, we showed that in a much more precise way, how this distance function changes, sort of controls the oscillation of the set, controls the flatness and smoothness of the set. But that's sort of not particularly important. Oh, but this is actually kind of fun. It's a sort of fun thing to be able to prove that if this distance function if its gradient never changes size, so if it always grows at the same rate, then your original set has to have been just a straight line or flat. So we have a sort of convoluted math proof of this, but I'd be interested if the physicists sort of know why this is true intuitively. It's not so clear to me. I can bring this up later. Okay, so let me just sort of give you a couple more characters, and then I'll get to the punchline here. So we have our graph, which we think of as a curve inside of some large space, R3. We have the smoothed out distance, and now we have the operator, which is the simplest possible operator with the Coulomb that we were talking about before, right? It just sort of says Brownian motions come towards our thin set, and it attracts it by dividing by the distance. And then Guy, Svitlana, and Josef were able to prove that indeed this sort of forward direction, that nice geometry implies nice solutions to the PDE, is true. That if you're the graph of a nice function, a Lipschitz function that doesn't oscillate too wildly, then this k of x, this Poisson kernel, sorry, k and f became the same thing again, is never too small or too big too often. Okay, so this is the forward direction. This is question 1 that we were talking about in the higher codimension setting. Notice that it applies to a much more general sense, so you don't need your Coulomb to just look like this, but it can look sort of like a smooth perturbation of this. Okay, and now what about the other direction, right? If I know that the Poisson kernel is nice, if I know that I can solve the PDEs well, does that mean that the geometry of my curve is also nice? That's exactly what I said here. A baby case might be if I know that my Brownian traveler is attracted equally to every point in the set, does that mean that the set has to be flat? Right? That's another way of saying it. The answer is unfortunately no. So the picture, which was so beautiful in codimension 1, is completely messed up in higher codimension. So let me talk about that very briefly, and then I'll let you go. So here's a joint result from earlier last year with Guy and Svitlana. It turns out that for any curve you draw, no matter how nasty it is, as long as it doesn't look sort of too terrible at every scale, this is this Lipschitz condition, then there's a way to paint the curve with Coulomb such that Brownian travelers will see every point of the curve equally. So in codimension 1, you could only see every point of the curve equally if you were the center of a ball. And now here we have a way of painting the set such that you could always do it, no matter how nasty the set is. We even have a version of this theorem for when E is a fractal, so like the snowflake that I was talking about before, but there are some more technical conditions. You can't guarantee constant proportionality, but rather just so that one is comparable to the other. And as I was saying, in codimension 1, this is certainly not true. There's a lot more rigidity. So what's the takeaway? In codimension 1, the solutions to PDE characterize the geometry of the domain. And at least in higher codimension, for this particular way of creating Coulomb, this is not true, and it's not true in the most spectacular way possible. Right? It really doesn't tell you anything about the geometry in any way, shape, or form. Okay? So in some sense, the Coulomb is too good. It makes the whole set too attractive. So let me briefly talk about this magic value of alpha. So this result that I was talking about on the last page is only true in codimensions larger than 2. So you can think of a line inside of R4 or something like that. And now I know that I'm sort of losing people immediately, but I sort of want to point out something which maybe everyone can take home, which is the following. By complete accident, we came up with a value of this regularized distance such that the distance itself is a solution to the PDE. And that's true outside of any possible set. So before, when I was sort of hammering home how hard it was to compute a Green's function, here we were able to compute a Green's function for this domain, no matter what the domain is. So this d alpha is in some sense a Green's function. And this is a sort of very surprising coincidence that we don't really understand at all. So let me maybe zoom through here. I'll just say one other thing, which is that for this special value of alpha, when alpha equals n minus d minus 2, we're sort of integrating this fundamental solution to the Laplacian. And so maybe there's something about the fact that this is a harmonic function. And we can sort of talk about that later in private if you'd like. But sort of the upshot of all of this, and maybe I'll move through these kind of quickly, is that we don't know anything about why this situation happens. We're totally stumped. And so part of the reason why I gave this talk is so that we can open up lines of communications about the codimension 1 situation. But I'm also interested to know if, as physicists, you have any intuition for what's going on in this situation. So essentially, we're able to prove our theorem because we computed that this distance function satisfies some sort of PDE, but we don't know why. We don't have a physical or a geometric or a probabilistic interpretation. And we would love for someone to say even something like, hey, this looks vaguely like this other thing, which is a well-known thing in physics or geometry or probability. And we have lots of very basic questions about whether or not other smoothed out distances are magic, whether or not this is a persistent phenomenon or it's only true for this particular choice of coefficients. There's lots of things we don't understand. And we're very interested in the answers to these. Okay, so I think we're sort of hungry enough to, or not hungry, but we're ready to be done with the day. So thank you very much for listening. This is Rue Laplace, by the way, which is on my way from my Airbnb to the conference. So I was very taken with it this morning.
Thank you. Well, thanks a lot, Max. It was a beautiful presentation, which warmed my heart for obvious reasons. But I hope everybody else is too. Any questions, comments?
Yeah, so from what I get, alpha is a number.
Mm-hmm.
It's a number.
It's a number. Yeah.
But so what I don't get is that if you have your curve, which is winding in a certain way in this part of the space, and it's very different, and that alone would be an alpha 1, and then you glue it to another curve which would have an alpha 2. So what happens?
So the problem is that alpha actually doesn't depend on the curve at all. It's a number which depends only on the dimension of the curve and the dimension of the ambient space. So every curve in R4 has the same alpha associated to it, which is strange, right? So you could believe that if you told me the set ahead of time, I could come up with some strange way to attract Brownian travelers to every part of the set. But I'm not cheating in that way. I first tell you how I'm going to attract the travelers, and then you give me the curve, and I'm still able to attract them equally to every point.
That's the strange thing. Any other questions?
Well, maybe I should ask. So what about this borderline codimension 2 case? I mean, is there a chance that there's actually a limiting formula? I mean,
So,
is rather than codimension 3?
I think there's very much a chance. I mean, let me even be sort of more bold. Let's say in codimension 1, I think it's possible that if you allow for strange coefficients of diffusion, no matter what the geometry of your domain is, you could find a random process which talks to these coefficients of diffusion that hits every point on the boundary the same way. And I don't think anyone knows this at all. So that I think is a very concrete question which maybe should be of interest to a more broad swath of the audience.
Is there a relation between that codimension 2 and the fact that a sole FH1 function that doesn't have a trace on codimension 2? That's the limiting point?
That relationship is closer to this idea that Brownian motion doesn't see sets of codimension 2. Honestly, we understand this result so little that I can't really tell you like what the codimension 2 really is related
So
to.
in the statement you just made that the Brownian motion doesn't see codimension 2, is that
That's the same effect.
directly tied
That's
to-
Yes,
point blank the
it's
same.
essentially the same,
Point blank
the same statement. Yeah,
It's point blank.
Okay.
yeah.